Okay, so speed, velocity, and acceleration. Let's do a quick review of the stuff that you will be practice tested on over the weekend.
This race brought to you by Visa, the official car.
Everything is about this guy. Speed and velocity. Lecture hinges upon that guy. All right, so Michael Johnson, 1996 world record holder in 200 meters. And there was a second guy who broke the world record in 100 meters a couple of years later. His name is Green. And so people debated before saying Bolt, which one was faster? Who was faster? Was it Johnson or was it Green? So we'll just settle that debate. All right, so this semester we're doing is mechanics. So it's the study of motion, description of motion, kinematics. And everything in physics, every time you have to come up with a theory, it needs to be expressed in the form so that we can make measurements. All right, so which means that we need to come up with a definition. And definition is going to have things that we can measure. So motion is expressed in terms of displacement on mass and space and time. So mass, time, and space, they need to be expressed in terms of the way we actually measure things, right? So what's time, for example? Einstein came up with the best definition of it. Einstein says time is what's measured by measuring stick. Time is what's measured by a clock. Space, in your mind, it could be one-dimensional. So right now we're doing kinematics in 1D, for example. It could be two-dimensional, so it's going to give you an area. It could be three-dimensional, so it's going to involve a volume. If it's the string theory, it could be 10-dimensional or 11-dimensional. All right, regardless of the number of dimensions that you may have, you still have to express each and every single dimension in the way you measure it. And once again, Einstein's got the best definition for space. He says space is what's measured by a measuring stick. The last one is mass. Mass is not what's measured by a scale, which you're measuring by a scale is your weight. It's not the same as mass. Mass is evidently related to something called inertia. The concept goes back to Newton. In reality, it goes all the way back to Galileo. So the measure of inertia is known as mass. Inertia is related to tendency of an object to retain its initial speed and then the direction of that speed. That's it. All right, so now that we got our basic definition of motion, now we have to express it symbolically so that we can build up theories using symbols. So object is getting displaced along the x direction within this time period. So it's got mass, m is going to be your mass, x is going to be your distance, and t is going to be your time. All right, everything is going to be expressed in terms of metric units or standard international units. All right, so mass is going to be expressed in terms of kilograms, distance in terms of meters, time is going to be in terms of seconds. And then we'll employ MKS unit system. M stands for meters, K stands for kilograms, and S stands for seconds. So that's what we'll do. And then distance versus displacement. Distance represents the total distance, total path traveled in this case. All right, so I've done some little bit of sightseeing last year when I was working full-time in California. It's a full-time temporary. Currently, I'm in Texas. All right, working near Houston, full-time faculty member, Brazos Sport College. And still living in Chicago, so I have to travel back and forth. All right, once a week. Usually, that's what I'm trying to do to teach the labs there. The lectures are still online. All right, so on Thursday is my traveling day. So last week, my plane got delayed, so we didn't have a recitation session. But obviously, we will keep doing the recitation sessions on a regular basis. All right, so I end up working somewhere in California. It was more like here than San Diego. It was Visalia. So now, if you're looking at the shortest distance between 2 points with the final location indicated as an arrow, that becomes a position vector. All right, and so otherwise known as displacement. All right, so all of a sudden we got definitions like distance versus displacement. Distance is a scalar, displacement is a vector. So we need to know what a scalar is and what a vector is. Scalar is just a number. Anything that is magnitude is known as a scalar. Anything that is magnitude only is known as a scalar. So from what you guys are looking at, so temperature is a scalar, pressure is a scalar. Vectors is anything that has magnitude as well as direction is known as a vector. Right? So acceleration is a vector. You can speed up in the forward direction and slow down in the opposite direction. All right, so we're jumping into physics. So speed, how fast an object moves in space and in time. All right, so for a given time, say like 20 minutes, the guy who's driving faster is going to end up traveling further away, right? So you know that speed is going to be directly proportional to distance or displacement. And for a given distance, say about 30 miles, the guy who's driving faster is going to take less time to get there. So the person who's driving faster is going to get there sooner. So you got this inverse relationship between speed and time. All right, so that's pretty much how you start out by formulating these concepts. All right, so we came up with our basic symbols. So speed is going to be directly proportional to distance. It's going to be inversely proportional to time. All right, instead of using S, we use V because this is going to turn into velocity at some point. So distance is in terms of meters, time is going to be in terms of seconds. So speed is going to be in terms of meters per second. All right, and then in the United States, we use the British unit system. So things will need to get converted to the numbers that we understand. All right, a couple of bad habits that we will have to stop breaking immediately. The sooner you break it, the less painful it's going to be for you guys. because on the testing, first couple of tests are formatting tests. I just want to make sure that you guys get the format right before we can start building upon on that format. And then you will thank me later when you guys start taking more advanced engineering and physics courses, because let's break the bad habits from my school. That's one of the first things. All right, so use the standard formulas. You will find the standard formulas on the formula sheet. Another thing that get used to doing conversions. Whenever you're done with a problem, convert things to the units that make sense to you. Physics is not an excuse to teach you math. It has nothing to do with it. And physics is not applied math either. All right, there are concepts which are summarized using these formulas, and that's the extent of it. And we use formulas, symbols, or whatever in order to generate numbers. And then we get numbers from experiments. So good math is required, and show work is 100% required. And when you come up with a number, you got to interpret the number. There's a reason why you're solving a problem, because you're curious about something. So make sure that there's a conversion to something that you understand. Most people in the United States, me included, understand numbers better in terms of British unit system. So you're used to doing the conversions. All right, case in point, the example that we looked at during the lecture
goes without machine power.
All right, so you got Johnson.
Johnson smashed the world record with a time of 19.32 seconds.
19.32 seconds for 200 meters.
Under 10 seconds.
Versus this guy, Green, 100 meters within 9.79 seconds. So who's faster? Okay, so a couple of things which is going to happen. Okay, so I have a non-traditional teaching approach, obviously. I don't want to give you the theory, boom, 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 and let's solve some example problems. And then you look at the back of the book and then you move forward. Okay, that doesn't really promote any understanding. All right, my approach, I work in an art school. Those of you guys who watch the videos, lecture videos, should know that by now. My style is I'll find something from real life, pose it as a question. We will investigate. In doing so, I'll introduce the concepts that we need and develop the concepts from there. And then stuff that I introduce into the lectures is main observations. They will become your conceptual test questions. All right, test will have 4 sections. One section is short essay conceptual questions, and you will struggle, guys. If you're not paying attention, you will struggle. This is not something you can Google. This requires understanding. Understanding is not something that you can Google. The information you can, but it's not going to help you in this case. All right, so the question is, who's faster? Is it Johnson or is it Green? You can take a high school approach, okay? So I'm just going to skip the formatting right now. I'm just going to move on to the end of it. You come up with a number in terms of meters per second, and then convert it to miles per hour. Immediately, something pops up. You go, oh, these guys are running over 23 miles per hour, and it doesn't seem that fast, right? Because you guys are used to driving. Try to run at that speed. Check to see if you can get up to 20. And I can tell you that unless you're a sprinter, you cannot get up to 20 miles per hour, guys. Maybe less than 1,000 people can run at that speed, around 20 miles per hour. It's not that easy. And then you repeat the same thing for Maurice Green, and then boom, it's almost like high school physics. And then come up with a number for him, it's going to be under 23 miles per hour. Johnson is over, Green is under, and then using high school mentality, you think you're feeling comfortable. Hey, you got the answer, right? Johnson's faster than Green. And then somebody's going to say, oh, yeah, really? If that's the case, how come Johnson didn't have the world record in 100 meters? That's a valid question. The only thing you know is Johnson's calculated speed is larger than Green's calculated speed. That's it. And then, in order to make matters more complicated, NBC News comes up and says, hey, Green's top speed was 27 miles per hour. When he was running 100 meters, his top speed was 27 miles per hour. So his top speed, measured speed is 27. And all of a sudden somebody says, yeah, you know, but the Green's top speed was like 27 miles per hour. So obviously it's faster than Johnson, whose calculated speed is 23 miles per hour, right? And life gets really complicated. Math alone is not going to get you anywhere in physics. Guys, you just have to really juggle a really good understanding of the concept. Definitions are really, really important. And formulas, obviously. Right? So I'll give you guys the basic formulas. The calculus formulas will come up soon. So it's faster, and how do you decide? One of the things that you need to realize that when these guys are running, they don't go from 0 to 23 miles per hour within one single step. All right? And while they're running, they don't keep at 23 miles per hour in the case of Johnson. So the speed is going to keep changing. So if it keeps changing, what does that computation represent? So the computation is going to represent your average speed. That's what it means. So measured distance over measured time is going to be your average speed. The only thing you know at this point is Johnson had a larger average speed than Green. That's it. Johnson had a larger average speed than Green. Yet Green's top speed is 27 miles per hour, and then 27 miles per hour is the measured speed. Okay, so instantaneous speed is the measured speed. So that's how fast you're moving at a given instance of time. That's what it means. So in the case of Green, they were using a radar gun in addition because they wanted to see what's the maximum speed that these people were getting up to, and they were amazed that this guy literally went up to 27 miles per hour. In the case of Johnson, no such thing. All right, no one was looking at the instantaneous speed. They weren't using a radar gun back then. So does this, given the fact that Green has a top speed which is 27 miles per hour, does that mean that he was actually faster than Johnson? That's a tough question. That requires a great deal of understanding of the concepts, and then it requires a good analysis regarding this question. All right, so each question you will have 2. randomly selected questions from these lectures, and you will have to answer the question, explain it, and then you have to justify it. It's a 3-step process. All right. And I'm not looking for poetry, just get to the point, keep it short, because you will have 5 minutes to answer that. So make sure that the main observations are things that you think about and make sure that they make sense to you. All right. And this is a skill that you will have to develop in this course. All right. Physics is essential. Engineering is applied physics. The better you understand physics, the better you will do your engineering classes. Those of you guys who are getting into physics, well, this is your introduction to how we do physics in real life. All right. So how do you answer a question like that? Let me give you the answer. Who's faster? Think of it this way. How do you decide who's faster in a race? Who's the fastest person? Well, whoever finishes up the race first, right? That's it. So what do you have? You got to measure distance, and then they measure each and every single person's time, and the person that finishes up the race first has the shortest time. All right. So whoever has the largest average speed is the fastest person. That's it. That's how it is done. So who's faster? It's an average speed to average speed comparison. That's it. That's how it is. It's been just like that forever. All right. That concept happens to have a name. The name of that concept is average speed. So if you're trying to figure out who's faster, it's an average speed to average speed comparison. Whoever has a larger average speed is faster. Johnson has a larger average speed, it's faster. And then the question is, well, gee, if he's faster, how come he doesn't have the world record in 100 meters? He doesn't have the world record in 100 meters because his acceleration is not as great. Okay, he doesn't get up to his top speed that fast. It takes, for him to get up to his top speed, he probably takes him 80, 90 meters for him to get up to his top speed. He doesn't have the same explosive acceleration as Green does. All right, so he's faster, but he's not quicker. Green is quicker, but he's not as fast. As a result, his average speed is lower than Johnson's average speed. So Johnson takes a little bit longer to reach his top speed. As a result, his average speed is larger. If they were doing a top speed to top speed comparison, I could almost guarantee you that Johnson's top speed is also larger than Green's. If Green is at 27 miles per hour, Johnson is 28, 29 miles per hour because his average speed is larger. All right, so that's it. So that's the sort of explanation that I'm looking for. All right, so answer the question, explain, and then you have to justify. All right, so while you're watching these videos, every single main observation is a test question you're doing. Velocity is different from speed in the sense that now you have to account for the direction of motion. I mean, what if you have two objects moving at the same speed while moving different directions? Would they still have the same velocity? They have the same speed. Obviously, velocity depends on the direction. So if the direction is not the same, velocity is not going to be the same. So basic introduction to vector calculus in this case. All right, guys. I don't know if I explained it in the videos. Let me just explain it while you guys are here. Calculus is prerequisite, but the sort of calculus that most of you guys, I think, can Calc 1 right now. I think it's a requisite. Some of you guys may be taking Calc 2. Calculus is a requisite for this class. It doesn't mean that we're using a lot of calculus. All right, a lot of the times you will learn the math and the calculus that you need for this class in this class. A lot of the calc that we'll do is going to be vector calculus. That's Calc 3. You won't be taking it anytime soon, obviously. All right, so in Calc 3, the vector calculus is more or less an extension of trig. All right, so I'll make a transition for you guys. If we were using calculus, most of the time we will get to use calculus in derivations. All right, so when I do derivations, I will use calculus, and I will add an extra link for that one. All right, not better than 90% of the time, 95% of the time, we're going to be using algebra and we're going to be using trig. That's how it is done at this level. When you move on to 300 level courses in physics or whatever, it's all differential equations and calculus, and you will still use a lot of algebra as well, but there's going to be heavy involvement from a higher math perspective in higher level courses. Okay, same is true in engineering courses as well. All right, so just because this is not, once again, physics is not an excuse to teach you math. All right, so it's calc-based, meaning that we will introduce concepts like vectors and then integrals and this and that, and a lot of it will be the basic concepts, just understand it. All right, so we're dealing with this known as vector calculus, obviously, the vectors. You got two objects moving at the same speed, they're moving in opposite directions. So how do we specify direction if that's the case? We've got to start coming up with some sophisticated symbols in this case. The motion to the right is going to be positive, motion to the left is going to be negative. Up is going to be positive, down is going to be negative. Okay, so this is to the left, it's going to be negative. Down is going to be negative. So this is negative velocity. So this one, does this mean that they both have the same velocities? Nope. Still, they're not moving in the same direction. And then now what we need to do is we need to specify the direction of motion using the x and y or z coordinate system, depending on how many dimensions we got. So the subscripts will indicate the direction of motion, and that's it. So these are the vectors that we will get to use. And then the vectors math is going to get sophisticated fairly fast. So we're just going over the basic ideas. All right. So in this case, what if we have something moving in a circle at a constant speed? Is velocity also constant? So I think you guys know the answer. The answer is no, because velocity is a vector, so the direction is going to matter. If the direction is changing, that's going to change the velocity. And so even if the speed is constant, the velocity may not be constant because the direction of motion is changing. Okay, so that's it from this section. All right, let me just run through this and then we'll do a review for acceleration. So what's motion? It's displacement of mass in space and time. Okay, so whenever you're watching the video links, just take notes on this one. This is your knowledge base. Okay, stuff that you will build upon. Okay, you just want to make sure that everybody's on the same page. Measurable quantities in describing motions. So obviously you measure mass, time, as well as space. Time is what's measured by a clock. Proper unit is again seconds. Space, what's measured by a measuring stick. It could be multidimensional or single dimension. Proper unit is going to be meters. Mass is measured every inertia. Proper unit is going to be kilograms. MKS stands for meters, kilograms, and seconds. Distance versus displacement. Distance, total path. Displacement is the shortest distance between 2 points, with the final location indicated as an arrow. Distance is a scalar. Displacement is a vector. It's got direction. Speed is how fast that object moves in space and in time. Proper unit is meters per second. Average speed is a computed calculated speed. Measured distance or measured time. Instantaneous speed is the measured speed. Difference between the average and instantaneous speeds. Average is a calculation. Instantaneous is a measurement. Velocity is not only how fast, also which direction. So it's a combination of speed and direction. So the difference between speed and velocity is the direction of motion. That's it. Okay, so my emphasis is something straightforward.
We crash it. We don't.
Crash zones, the crumple zones in these cars. All right, so it's a 40 mile per hour collision. The car is stolen.
Care about.
So what's the purpose of a crumple zone in these cars? The answer to that question is straightforward. It's safety, right? All right, we've got crumple zones because they're meant to make you safer. So a couple of questions regarding that. How? Okay, how does that make you safer? Having a crumple zone in a car, how does that make you safer? And if the whole idea of having a crumple zone is to make it safer, why not just make the outside indestructible and put the safety on the inside? Why not do it that way? Okay, these are test questions usually. All right, so the whole idea of the crumple zone is to reduce the acceleration on your body. All right, it's related to acceleration because the acceleration is what kills you, what maims you, and what breaks your bones. And the acceleration, we try to express acceleration usually in terms of G's. G is your own body weight, for example. Prolonged exposure to 75 Gs, for example, it can kill you. So the question is, so what happens inside the body, in essence?
Blackout.
The one that you guys have seen in the lecture is this guy, happens to be a medical doctor. He's inside a centrifuge, he's exposed to about 7 Gs at this point.
First thing that happens is blood flow begins to be reduced to the head. So you begin to develop a tunnel vision. The next thing that we see is loss of motor control.
I mean, he passed out at 7 Gs. That's what happened. He's got a bit of an explanation as to what's going on in his body. He's a medical doctor. He's not a physicist. He's in the ballpark, but his explanation is not very accurate. So something about the blood flow, but his interpretation of how the blood flow happens has nothing to do with reality. All right, so why is he passing out? The reason why he's passing out is because of something that you can relate to, something that you experience. It's related to acceleration. So you speed up, the car accelerates in the forward direction, you feel it pushing the opposite direction of the acceleration of the car, right? And then you put the brakes on, the car is slowing down, now you feel it pushing the forward direction. So all of a sudden you realize that the objects inside the vehicle will move in the opposite direction of the acceleration of the vehicle, right? All right, so that's one of the things that you notice. The objects which are not strapped down inside vehicles will always move in the opposite direction of the acceleration of the vehicle. They will always move in the opposite direction of the acceleration of the vehicle. All right, so notice that Jesus is trying to keep up with his cross because of the acceleration. The acceleration could be a religious experience. So just imagine that I'm driving my souped up tempo in the forward direction at 7 Gs. What happens to my body? My body's going to move in the opposite direction of the acceleration of the vehicle. So these are test questions. What happens to the blood? Once again, it's going to get pushed in the opposite direction of the acceleration towards the back of my body. Likewise, what happens to the blood in my brain? Same thing. So the blood is going to pull away from the frontal lobes towards the back of my brain, right? So lack of blood in the frontal lobes, lack of oxygen, eventually you will black out. So that's what happened to the guy. Except there's a slight catch here. This guy wasn't really speeding up or slowing down. He wasn't inside a souped up Ford tempo accelerating at 7 Gs. This guy was probably moving at 60 miles per hour at a constant speed inside a centrifuge while experiencing 7 Gs of acceleration. And all of a sudden you go, wait a minute, this is weird. How is that possible? Because based upon what we saw so far, it's speeding up his acceleration, so it's slowing down, but this guy is not speeding up or slowing down. The only thing you notice is he's just changing direction, right? So could it be that the change in direction could also be interpreted as acceleration? All right, so listen. So we can run a simple thought experiment. Obviously, you got a pendulum. So the car accelerates in the forward direction. Pendulum moves backward, that's acceleration. So speeding up is acceleration. And then you put the brakes on. This time, the pendulum moves forward as you're slowing down. So slowing down is acceleration. And then when you're on a curve driving like that, once again, you look at the pendulum, check to see what happens to the pendulum. Notice that the pendulum swings away from the center of the circle. So which means that this is the change in direction is also acceleration, right? So acceleration points in the opposite direction of the motion of the pendulum. So which means that it's going to be directed towards the center of a circle. This is known as the center seeking or center directed acceleration. The technical term is centripetal acceleration. So this guy, the medical doctor inside the centrifuge, was sitting up. It was an upright centrifuge, meaning that he was sitting up with his back against the wall. So the acceleration is directed towards the center so that the blood will be pulling away from the center towards the back of his head. Okay, once again, guys, everything that I'm describing, these are test questions, all right? The guy ended up passing on the inside centrifuge. The question is why? Because the blood was moving in the opposite direction of the acceleration of his body. All right, so the circular motion, the acceleration is directed towards the center. So all of a sudden we have a more encompassing definition for acceleration, right? So speeding up is acceleration, so it's slowing down, so it's changing direction. So the combination of speed and direction is velocity. So we could say how fast the velocity changes in time. All right, so mathematically, it's an easy thing to model. Changing velocity in time, so initial velocity to final velocity within this time period. And A is your acceleration, V is your final velocity, VO is your initial velocity, T is your time. Velocity is in terms of meters per second, so it's going to be meters per second divided by seconds, so it's going to be meters per second squared is the proper unit. And for safety reasons, we'll express this in terms of G. Roughly about 10, this is a wiggle, it's a 10. So it feels like your own body weight. All right, now let's make it a little bit more abstract. Okay, so the same ideas will be expressed in terms of using differential calculus, but get used to the basic ideas first. The stuff that you need to know here is what's changing here. Is it the average speed or is it the average, is it instantaneous speed? What's changing? Is it the average velocity or the instantaneous velocity? And this time, what does that time represent? All right, so VO and V, okay, VO represents your speed right at this instant. So if you're driving like a car, check to see how fast you're going, let's say about 40 miles per hour. You look down at the speedometer, this is your reading right at that moment. So this is your instantaneous velocity at that point. And then a couple of minutes later, you look down and check to see if you're still moving at the same speed. This just so happens you're not. You're moving at 50 miles per hour. All right, so what's changing is your measured velocity is changing in time. Your measured velocity is changing in time here. T represents the time period between two measurements. All right, so you take the first measurement, and then a couple of minutes later, you're taking the second measurement. So how fast your instantaneous velocity changes in time becomes your average acceleration. So this computation is only going to give you your average acceleration. All right, so acceleration is going to be a vector, which means that it's going to have a direction. Positive acceleration means it's speeding up, something is speeding up. So the positive acceleration usually happens along the direction of motion. All right, if it's acceleration is pointing along the direction of motion, it's going to be positive. Final velocity is going to be larger than the initial velocity. Negative acceleration means that the object is slowing down. Acceleration is usually pointing in the opposite direction of motion, which means it's slowing down. The initial velocity is larger than the final velocity, whatever what that means. All right, so in terms of concepts, John-Stafford experiment is important.
No one has ever undergone such a test before or since.
In terms of concepts. It's a crucial experiment. This guy's crazy. It's a crucial experiment. So this guy straps himself onto a rocket sled. And then he's accelerated up to 632 miles per hour. And then they put the brakes on. And they brought him down. They will bring him down to a stop within 1.4 seconds. All right, so within 1.4 seconds, it's brought down to a complete stop. All right, so car companies wanted to know what's considered survivable for a fraction of a second. So that's the purpose of this experiment. So John Stapp volunteers for this experiment. He's in charge of it. This guy's a medical doctor. He must have conducted some animal experiments. And he was exposed to 20 Gs during this experiment. The damage was his retina got detached. And then eventually he recovered his vision. And then he keeps repeating these experiments and looking for some kind of an upper threshold. And then he discovers that around 25 Gs, you're going to start to break bones. So the car companies get what they were looking for. They noticed that you can survive up to 28 to 25 Gs for up to a few seconds. That's an important finding. All right, 20 to 25 Gs up to a few seconds, you can survive.
Just after the impact. That's only about 2 seconds.
And then they start building their cars around that number. They started building their cars for impact around the number of 20 to 25 Gs at reasonable speeds like 40, 50 miles per hour.
Newspapers have talked luridly of speeds of 120 miles an hour, but looking at the damage tells a very different story. It suggests an impact with the pillar of about 60 miles an hour.
And then their focus is the Princess Diana's accident. All right, so if you're driving by, if you see a car like that, and you would expect people in the car to be dead. And it wouldn't surprise anyone that you have 4 people, 3 of them are dead. You would be surprised that even one person survived that. And then when you find out that the survivor was in a coma for about a month, you go, okay, then that makes sense. All right, that's the way you would look at it because you guys have a lot of common sense. And common sense is no substitute for education. When I'm driving by, when I look at something like that, I would look at the damage and I would say, oh, I would think that every single person in this car survived the accident because the car did its job. It's completely crumpled. This is the engine compartment. The engine compartment is supposed to complete this, gets smashed, it's supposed to crumple, it's supposed to
Know
crash.
that the car came to rest about 15 feet from the pillar, spinning out, and that means about 10 miles an hour exit.
All right, so they estimated a bunch of stuff. These are the accident investigators. Here's what they came up with. They realized that the estimated speed of the car by looking at the damage, this is like 60 miles per hour. By looking at where the car ended up after the impact, they estimated that the final impact speed was 10 miles per hour. So change in velocity is 50 miles per hour. And the impact time that you're looking at, this is an estimated impact time, which is built into the car, it's built into the crumple zone. At 40 to 50 miles per hour, it should give you about 10 to the second. And this is at 50 miles per hour. So estimated acceleration of the car was about 22 Gs. That's the average acceleration of the car. It was about 22 Gs. Is that considered survivable? Are you kidding? Really? John Stapp survived something like this. Up to 1.4 seconds, guys. That's a duration which is 14 times longer than this one is. All guys survived this. Up to 1.4 seconds. And the damage was his retinas that temporarily detached. That's it. His soul did not detach from his body. His retinas got detached. That was the extent of the damage. Yet you have 4 people in this car and 1 survivor and 1 person barely survived and 3 people dead. So what's going on? Well, you get the impact time from the crumple zones. Crumple zones usually should have at least 10th of a second built into them at 40 to 50 miles per hour. Without the seatbelt, your impact time is not the same as the cars, right? They 3 people who died, including Princess Diana, obviously. None of them were wearing seatbelts. None of them. If you're not wearing a seatbelt, you get your impact time from whatever it is that you had and whatever it is that you can break within your body. Okay, so it becomes a problem. The worst case scenario, your impact time is going to be 100th of a second. If you're hitting a dashboard, steering wheel, without a seatbelt, you're on your own. Change in velocity is still the same as the cars. It's 50 miles per hour, except the impact time is much shorter. And acceleration is way over 200 Gs under the circumstance. Not survivable. The car's impact time is 10th of a second. It comes from the crumple zone. And the unbuckled passenger's impact time is going to be shorter than the car's impact time. So car's acceleration roughly 20 Gs. And if you're not wearing a seatbelt, the worst case scenario is going to be over 200 Gs. That's it. So what does the seatbelt do for you? Well, the seatbelt attaches you to the car. That's the purpose of the seatbelt. So you have the same impact time as the car does. All right, so these people experienced some over 200 Gs, all of them. So the next question is, what's considered survivable? Based upon accident records that they obtain from these collision scenes or whatever, black box data, either the race cars or even the regular commercial accidents, okay, they pull out the data, check to see what the numbers were. And then sometimes people survive, and when they do, they look at the numbers, all right? 20 years ago, it was around 100 Gs. Today, the numbers are around 140 Gs. Under extreme constraints for a fraction of a second, you can survive. You may be able to, under extreme constraints, up to 100 to 140 Gs. All right, anything over 140 Gs is not considered survivable. All right, so why not build indestructible cars and put the safety on the inside? Okay, so when I'm talking about putting safety on the inside, I'm talking about airbags, obviously. That's what the smart cars usually use. All right, what happens to the impact time if the car is indestructible? Impact time is going to be infinitely small, which means that the acceleration is going to be infinitely large. So wearing a seatbelt is not going to help you under the circumstances. It makes it worse. And so what if you have airbags instead on the inside? So the question is this, guys: when do you deploy the airbag if the impact time is non-existent? Airbags are usually deployed within the impact time, within the span of that impact. All right. If you don't have an impact time, you don't have enough time to deploy the airbags. Okay, that becomes a problem. Of course, we have AI-driven cars today, highly intelligent cars with sensors and everything else. They can kind of estimate when the accident is about to happen, and they can deploy the airbags ahead of time. And the problem with that approach is you also got your reflexes. All right, reflexively, you can avoid the accident. And while you're reflexively avoiding the accident, the airbags can pop and it can kill you. That sort of stuff is dangerous. So what does the airbag do for you? The airbag is designed to increase the impact time almost up to a second. Okay, so now take a look at the numbers. We're still focusing on Princess Diana's accident. All right, so change in velocity is still 60 miles per hour, 50 miles per hour. So with the airbag, it's going to be about 2 Gs. With the seatbelt alone, it's going to be about 20 Gs. And no seatbelt, no airbag, it's going to be a little bit over 200 Gs. And all of a sudden, you're taking a risk of doing a collision, which is almost 100% survivable. Okay. Side impact collisions, collision by collision, they tend to be the deadliest. 1/3 of the fatalities usually happen because of side impact collisions. Obviously, you don't have much of a crumple zone from the sides. All right. If you have a fairly new car, modern car, anything built after 2015, I think it should come with side impact airbags. Regardless of airbags or not, a couple of things to just focus on. Try to avoid direct impact to your body. Don't worry about the car, avoid direct impact to your body. All right. So this is usually what causes fatalities. All right. If the frontal portion of the car takes a hit, the car is going to spin. If the back portion of the car takes a hit, the car is also going to go into spin. Spin accelerations tend to be survivable. Maybe if you broken bones, whiplash, you may pass out. It's a formatting problem, and I want you guys to get used to the format. So this is MiG-28. All right, so while you're reading the problem, make sure that you got the proper symbols. So the first thing you have to do is just list everything. So this is a fighter jet traveling at 800 miles per hour for a distance of 155 miles. So what is the time? How long does it take for it to travel that distance? All right, so I listed everything and used the proper symbols. All right, the next thing you need to do is list everything given and put a question mark next to the unknown. Okay, so I listed everything in terms of what's given with their proper symbols and whatever the numbers are. The next thing you need to do is just do the proper conversions, do the conversions to proper units. Okay, don't take shortcuts. Okay, you'll thank me later because the real life is you will have units expressed in all sorts of different ways. Make sure that before you do anything else, and especially for you guys, the engineering students, stick with the standard international unit systems. All right, in engineering, they allow you to use these mixed conversions and all over the place, and mistakes become costly. You can lose your jobs over something like that. All right, it could be costly. Just stick with the standard international unit system, and then do your conversions back and forth at the end. Miles per hour to meters per second, miles to meters. I want to see work for a while. So do your conversions the way I do it. I like the way the chemists do it because it's easier. You can see what's going on. So miles per hour to meters per second, miles to meters. All right, so conversions you will find. Hey, Ziggy, move. You will find the conversions at the end of the formula sheet. And then obviously this is going to multiply the top, everything is divided by the bottom in both cases. And the next step is simple algebra. Okay, start off with a formula from a formula sheet. Okay, don't look things up somewhere else. Use a formula from the formula sheet. These are the standard formulas. Always start off with a formula. And then I'm not going to let you guys use numbers. This is not engineering, this is physics. Don't use any numbers until you come up with one final equation where whatever it is that you're computing is completely isolated on the left-hand side. So this one is completely straightforward. So T is what I'm looking for. Boom, boom, boom. One single step. I take a shortcut. T's on the left, and then always use numbers in terms of the metric units. And then it'll give you a standard answer in terms of seconds. This is roughly about 700 seconds. And then what you need to do is you need to convert it to something that you can relate to. All right, 700 seconds. No one can relate to something like that, obviously. All right, doesn't mean anything. So convert it to minutes, hours, days, years, light years. I don't care what it is. Just come up with something that you can understand, because there's always going to be a question at the end that requires you to analyze what you just came up with. All right, so that's pretty much okay. We're done that. So let's just go back to the lecture review. Per unit, meters per second squared. G is the expression of acceleration in terms of your own body weight. Unstrapped objects will move in the opposite direction of the acceleration of the vehicle. Speeding up is acceleration because unstrapped objects will move in backward direction. Slowing down is acceleration because unstrapped objects inside will move in the forward direction. Even if you're moving at a constant speed, if you're changing direction, you're accelerated. Once again, the unstrapped object will be sensitive to that sort of motion. They will always move in the opposite direction of that motion. Proper definition of acceleration is speeding up, slowing down, and changing direction. So it's a combination of speed and direction. So it's how fast the velocity changes in time. All right, so 7 to 12 Gs are survivable, considered survivable up to a few minutes based upon the pilot training experiments. In reality, you could probably go up to 15, 16 Gs. The good old days when they were training NASA astronauts for Gemini missions, they used to pick astronauts who can handle like 14 to 15, believe it or not. Okay, so how many Gs are survivable for 3 seconds based upon the John Stapp experiment? All right, so John Stapp experiment was conducted between 20 to 25 Gs. All right, so that range is considered survivable. For a fraction of a second, based on the data obtained from race car crashes, you can survive up to 100 to 140 Gs for a fraction of a second under extreme constraints, guys, under extreme constraints. I mean, you gotta make sure that you have the head and neck protection for something like that, or else it can, if you don't have a proper constraint, you can snap your neck. What would happen if the acceleration, what would happen to acceleration if the cars were made indestructible? The acceleration would be infinitely large, nearly infinitely large, so it would not be survivable. Typical acceleration during a car crash at 40 miles per hour. It's about 20 Gs. For people wearing seatbelts, it's going to be the same as the cars. It's going to be 20 Gs. No seatbelt, your impact time is shorter. It could be around 200 Gs in the worst case scenario at 40 miles per hour. Airbag, the airbag is about 2 Gs because the impact time is roughly about a second. Side impact collisions tend to be deadlier than the frontal impact collisions because of lack of crumple zone from the sides. So which means that because of the lack of impact time. There's an impact time, but the impact time is not large enough. You avoided deadly side impact collision by avoiding either hitting people directly or trying to avoid direct impact to your body. That's it. Okay, so that's as far as it's going to go. Okay, so this is the one that I was talking about when you guys came in. So this one is about the lab that you get to do. So average instantaneous speeds, 50 plus measurements that you take at 10 to 15 seconds or so from the speedometer. So those are the instantaneous speed values. And your average speed is going to come from your total distance measurement, and then your total time measurement for that trip. All right, so you will have two average values. One is the average speed computation. The other one is the average speed of the instantaneous value. So you do a comparison between the values, which is known as percent difference, divided by the average of these two values. You take the absolute value of it and multiply by 100%. It should give you your percent difference. Depending upon the number of measurements that you have, the bigger the number of measurements that you have, the closer your average of the instantaneous speeds should be to your average speed value. All right, so that's what you're verifying.